I have written the last result I obtained. I limit myself to put an apex here in order to distinguish vectors. Symbology is not exactly the same of the lectures, but however, the theory is the same. Well, left is the result. Clearly, this vector x prime, which is an element of A, can be expressed in this way as sum of certain x prime h, where x prime h is referred to xh for every h. This by construction of the set A. I maintain that according to this price system, in reality, every point x prime h must have a greater value than xh. And therefore, our theorem is proved, because this is exactly the thesis of the second theorem of welfare economics. We know for the moment only that the sum of these inner products is greater or equal than the sum of these inner products. But in reality, given our properties, it is possible to demonstrate that for every subject, this inequality holds strictly, and therefore, the original Pareto optimum is an equilibrium allocation. How is it possible to demonstrate these? By using, first of all, continuity and this last property. It does represent the situation of any subject, H, say. The vector xh is this, for example. This is the set of preferred elements of xh, and here there is x prime h. Is it clear? X prime h, which by construction is referred to xh. No problem. But by our last assumption, you note that this x prime h must be an element of a positive order. Right here. In other terms, x prime h must have all positive components. Therefore, since this point has all positive components, put attention, it is possible to move from this point in any direction for a stretch, and you will remain in the positive orbit, because this vector has all positive components. Moreover, since preferences are continuous, you, by moving in any direction, you will remain for a stretch in the set of preferred elements. This is the exact point in which continuity and this last property intervene. Is it clear? You can move from x prime h in every direction for a stretch, which you will remain in the set of preferred elements of xh. In particular, suppose of moving in the direction minus p. Minus p. This is a vector. This is a compass vector of a price system. which has at least one non-null component. Consider the vector x double prime h, which is defined in this way. X prime h minus mu times p, where mu is a positive number. In other terms, you move in this amount mu in the direction of price system. When you pass from x prime h to x second h. Is it clear? Well, if the movement is small, also this second point will be an element of pH of xh, will be preferred to xh. For a small mu, you have x second h is preferred to xh. Is it clear? Well, put attention. This is a fundamental point. Sorry. No, another step. Then I shall repeat all this first part of the proof. Let us evaluate, according to the price system P, this vector. You have P times x double prime h, which is equal to P times x prime h minus mu times p squared. By multiplying p by p itself, you obtain p squared. But since p has at least one non-null component, this linear product of p by itself is always a positive number. So you have that the vector x double prime h has a value which is lesser than x prime h. In other terms, in this way, you obtain a bundle x double prime h, which is preferred to xh as well, but it has a lesser value than x prime h. This is a fundamental step in the proof. Well, I shall repeat. In the first part of the theorem, we arrived to this result. Well, but each point x prime in A can be expressed by definition, by construction, as the sum of certain x prime h, where for every h, x prime h is preferred to xh. You remember, this is nothing but the definition of a set A. I maintain that even if, for the moment, we know only that the sum of these linear products is greater or equal to the sum of these linear products, in reality, by our assumptions, for every individual, the inequality must hold strict, and therefore also an aggregate is strict. But the important thing is that for every side it holds strict. In order to prove this result, let us make another step in the proof, in the demonstration. Represent graphically the situation. Here there is xh. Here there is the point x prime h, which is preferred to xh. No problem. But x prime h, by our last assumption, is a positive vector. Moreover, pH is continuous. So you can move from x prime h in every direction for a stretch, and so you will remain in the set of preferred elements. by continuity and the fact that this point has all positive components. Among the infinite possible directions, consider the direction minus p. Direction which is equal to the opposite of a price system. Move in this direction by an amount mu. You obtain this point, x double prime h, which is nothing but x prime h minus mu p times p. Here there is x double prime h. This x double prime h is referred to xh as well. But compute its value according to the price system by simply multiplying both sides as a quantity by p obtained this result. The value of x double prime h is equal to the value of x prime h minus mu times p squared. But since p is a not null vector with positive and negative components is not relevant, p squared is always a positive scalar. You remember, by multiplying every non-null vector by itself, you obtain necessarily a positive number. So the value of x double prime h is lesser than the value of x prime h, because there is this term which is a negative one. And therefore, you obtain the desired result. You can find a bundle x double prime h which is preferred to xh, but at a value which is lesser than x prime h. Is it clear? But why? And why this construction, this computation? Because let us suppose about assume that there is a subject for which this inequality does not hold. You can answer. There exists a k such that p times x prime k is lesser or equal than p times xk. By combining this inequality with this inequality, referring to subject k, you obtain p times x double prime k is lesser than this inner product, and therefore of this inner product. You obtain this result. Simply by combining this absolute assumption with our previous theory for a particular subject k. So substantially this means you can pass from xk to x double prime k, which is preferred to xk, by saving some money. You can obtain, if there is a utility function, a greater utility by reducing your expenditure. Utility function do not necessarily exist, but however. Is it clear? There is a saving. The saving can be written this way: p times xk minus p times x double prime k. This is the sum you are saving for the k subject, but however, in the end you obtain a bundle which is preferred to xk. This is a fundamental point. Now, by means of a procedure which is this point familiar to you, redistribute this increase, this saving among all the other H-1 households. All the other households have initially this value at their disposal. The original abundance XH multiplied by P. You add to these saving, so to speak, divided by H minus 1. Just represent the situation. This XH for some side. This is the set of the points whose value is less or equal to XH. Here is the budget constraint. Add this sum for every individual, so that the budget constraint of subject H enlarges. But to this point, note by local non-saturation that here there is a bundle X, second H, which is preferred to XH, and whose value is lesser than this sum, because it is in the enlarged budget constraint. So you have exactly for every H different from K, P times X double H lesser than P times XK minus P times X double K of H minus 1. You obtain this result. Last step. Sum side by side every of these H minus 1 inequalities. You obtain on the left hand side sum for H different from K of P times X double prime H, and on the right hand side H minus 1 times this sum. P times K minus, plus here. Clear. It gets this term. Minus P times X double prime K of H minus 1 plus sum of H of P times H, XH. At this point, we can simplify these and these. H different from K. Then, this term can be introduced in this sum, and this term can be introduced in this sum. So in the end, you have P times sum for H which ranges from 1 to large H of X double prime H lesser than P times sum for h which ranges from 1 to large h of xh. But remember that every x double prime h is preferred to xh, and therefore this inequality, this is an element of the set large A, whose value is lesser than the value of this vector, in contradiction with the first part of the theorem, with the separating hyperplane theorem we applied in the first part. And by this contradiction, the second theorem of welfare economics is proved. It's a very difficult one. Now, write and then shall repeat this last part of the theorem. Right. Suppose that ab absurdum there existed a subject K such that P times x prime K is lesser or equal than P times xk. This means that there exists a vector x prime K preferred to xk whose value is not greater than the value of P times xk. So xk would not be demanded according to this price system. But by summing this inequality with the equality proved in the third part of the theorem, you obtain this inequality. The vector x double prime k, which is preferred to xk as well, as a value which is strictly inferior to the value of xk. In other terms, in sum, when the k subject passes from xk to x double prime k, you obtain a preferred bundle, but by saving this subject. Even if x double prime k is preferred to xk, however, its cost is inferior to the cost of xk. Is it clear? Now let us consider the situation of any other subject different from k. This is the value of a vector xk in the Pareto optimum, to which we had this saving divided by h minus 1. In other terms, this sum, which was spared, is divided in h minus 1 equal parts and distributed to the other side. The situation of the generic subject h is this. Initially, he had xh. This is the set of the points whose value is equal to xh. But after this subsidy is given, his budget constraint, so to speak, enlarges. By local dot saturation, you can find another point x double prime h whose value is inferior to the value of xh plus the subset. In other terms, this point x double prime h, which is preferred to xh, is below the budget line, which is determined by the subset. Now we have these h minus 1 inequalities. Sum them side by side. This is a simple mathematical step. So you obtain from the left-hand side this sum, h different from k. And from the right-hand side, you obtain this result. Note that this term is equal for every subject different from k, so you can simply multiply this term by h minus 1. The other is the sum of these p times xh. But this h minus 1 can be simplified, and then you simply Take this inner product, introduce it in this side. Take this inner product and introduce in this side. In the end, you obtain this result. Where the sums now ranges from 1 to large h and includes k. Every of these x double prime h is preferred to xh. But this sum of vectors is an element of large A, the set we defined in the first part of the theorem. And here it results that there is an element of A, this element, whose value is lesser than the value of this sum. But this in contrast with the first part of the theorem, with the separated hyperplane theorem, according to which every element of A has a value which is greater or equal than the value of this vector. Contradiction. And therefore, the theorem is proved. This is a very difficult theorem. But however, the fundamental point is convexity. It is convexity which permits us to introduce this price system which separates. And therefore, the remaining part of the theorem certainly uses the other properties, but they are substantially contour properties. The fundamental property is convexity. And so you could also the second theorem. Note, in the end, as I told you before, the fundamental difference among the first and the second theorem of welfare economics. Here, it is necessary to introduce very, 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 very strong properties about preferences for production sets, if you consider the more general case of a productive economy. But substantially, also in this case, we should suppose that production sets are convex as well. Another time, convexity. This theorem shows all the importance of this mathematical property for economic theory. It has